ودلوقتي عندنا examples on steady state conduction heat transfer. من ضمن الأمثلة المشهورة والممتعة إن إحنا نتناول قضية تسخين a body of water in a vessel which is on top of the fire. بنلاحظ إنه this is a situation wherein a flame keeps in touch with the vessel lower surface or the bottom surface. So if the flame reaches a steady state, so it motivates a steady state heat conduction. And if the body of water is stationary, so that's a pure conduction heat transfer without convection. ولكن على كل حال الظواهر حولنا تجمع العديد من التدخلات الطريفة والتي تستلزم شيء من التفكير والتخطيط في إعادة صياغة المواضيع طبقا للمنهجية اللي احنا ماشيين عليها. فلو حبينا نقول انه في body of water inside the bowl and the flame is at steady state while the temperature of its vertical walls slowly changes, so we have around the vessel there is natural air convection. The surrounding air is getting warmer when it touches hot bodies, so that this warmness is going to change its density so that it can set some slow motion, upward motion from the to raise the lighter bodies of air and replace with heavier bodies of air. So this is the natural convection. It's a slow motion, it's a slow mechanism for heat transfer. So if it's slow, so there is no forced convection, مفيش تيارات هواء قصرية حوالين الفيسل، يبقى معنى ذلك انه التبريد يتم بمعدل بطيء. فإذا كان التبريد بيتم بمعدل بطيء، يبقى معنى ذلك انه إذا قام الفليم بإمداد الفيسل بكمية من الطاقة so that temperature of the water everywhere is going to build up, to change, and because the molecules are in contact with each other, so that this is the conduction. So we can imagine that conduction will set the rate of variation of the water temperatures to be faster than the rate of variation of the vessel wall temperatures, because vessel wall temperatures are cooled by a slow process while the water is heated by a faster and stronger process. يبقى معنى ذلك أنا لو خدت سكرين شوت للحلة وفيها المية، أنا أقدر أراقب في فترات زمنية محددة إنه الباوندرز قد تثبت نسبيا عند درجات حرارة نتيجة بطء تغيرها، وفي تلك اللحظات هيكون الووتر temperature is able and is free to change by more drastic variation. يبقى الموضوع ببساطة تحول إلى إن أنا استطعت تقسيم الفترات الزمنية الحقيقية إلى فترات قصيرة يمكن تناول فيها steady state conduction على اعتبار إنه boundaries are nearly fixed within a time period، بينما التغيرات متلاحقة وسريعة جوه الدومين، فيمكن أن يسري تيار الكوندكشن خلال الووتر without movement so that it's conduction، ولكن تبقى الوولز ثابتة عند درجة حرارة ثابتة، فكأن المسألة مقسمة إلى عدد من steady state conditions. فبيسموا هذا التشويق quasi steady state analysis، إن حضرتك عندك شبه انتقال حرارة مستقر الزمني. يبقى في هذه الحالة we can write down the same equations, we can have the same analysis while taking into consideration that there are conditions. هو انه يبقى في تباطؤ في تغيرات احد العناصر المحيطة بالنظام، ويكون التغيرات بداخله اسرع، فيمكن ان تتم معالجة المسألة على انها quasi steady state problem. فتبص كده تلاقي it follows that the water temperature varies faster than the boundary temperatures. A quasi-steady state is thus considered across the body of water in the bowl. An easy task to work with these given numbers on the boundaries at this screenshot condition. So you can consider a two-dimensional domain. The boundary temperature values at the four edges are shown. The resultant equation that links any 5 neighboring points is, as we know, it says that the temperature of each point is the arithmetic average of the neighboring 4 points. So APTP equal AETE plus AWTW plus ANTN plus AS. We know how to work when we use the tridiagonal method. We concentrate on either the vertical direction or the horizontal direction, so that let us solve on vertical direction. So we are dealing with points N and P and S. So these are the unknowns involved when we consider the vertical line across which conduction will take place, considering that the eastern and western points should be at known conditions, so that we can solve the linear equations. To save the computer time, an engineer decided to solve half of the domain. So what should he tell the computer in this case to deal when we approach the axis of symmetry, so that we will only deal with half of the domain? We know that each thing on the right is identical to what is on the left, and circumferentially it is identical. So that in the two-dimensional plane, we know that around the axis of symmetry, everything is going to decelerate when you approach the axis of symmetry. When you approach the line of symmetry, you don't have to accumulate heat, because from the other side, when you issue from the central point, if there is an opposite accumulation of heat, then this point will burn. It will accumulate in heat, so that we don't have this unsteady state condition, but we have a steady state conduction. So everything at the point when you approach the line of symmetry should disappear. Nothing to give as a heat, nothing to lose as a heat, because if you lose, you will have a similar condition that you lose from one point in all directions, so that this point cannot be maintained at its steady state temperature. So there should be a state of art, there should be a method to tell the computer just stop dealing with the heat transfer when you approach the line of symmetry, because there is nothing to deal with the center of symmetry, the line of symmetry. Everything is going to be the same. So how you make similar points without stopping the heat conduction. So this is going to be something nice to tell the computer that just decelerate what's happening when you approach the axis of symmetry, so that you stop gently, and you will find your image on the mirror exactly as behaving in the same way, so that the line of symmetry is treated carefully. And another question is that you have to estimate values for the neighboring coefficients AE, AW, AN, and AS when there is a flow upward velocity from the top, from the bottom, so that you have boiling. So due to buoyancy, when you change the the liquid into vapor, its density is going to decrease, so that it will be lighter, it will come upward, so that there is an assisting motion to conduction. So is this going to change the relative contributions of my neighboring elements? Yes, it will. It will let your southern element pushing hard and harder than others, because it has an additional tool of supporting the heat transfer to communicate with this southern neighbor, because there is two mechanisms of heat transfer coming from this direction. So please give me an estimate values for the new values for the neighboring coefficients, and how much will be these values if the upward velocity is doubled, if you have excessive boiling and there is a continuous motion vigorously coming out to faster. So if we write down the equation, it's very nice that we have 5 temperatures to be involved, so that I link all temperature with each temperature with its neighboring 4 points. So as we have this equation, we will solve the unknowns Tn, Tp and Ts along the vertical direction, and we set Te equal Tw equal 30 as the background temperature. Therefore, if you substitute, now concentrate on the temperature Tn, it's the point of interest, so that it will be prepared by a coefficient of 4, so that it will be equal to the summation of other 4 points, and then they will be divided by 4. So please leave Tp as it is, because it's still unknown, while put the 30 3 times. So 30 for the western, 30 for the eastern, 30 for your upper neighbor, which is the upper boundary, so it's 30. So this will give 90. Now if you move to the point Tp, so now it's the point of interest, it has the coefficient of 4, so you will leave Tn and Ts around U, so that they are still unknown. And now you are left up with your eastern and western boundary, so that both of them are 30. So the equation will become one of the sides is equal 60. And the third equation, now you go to your southern boundary, so that your Ts is subjected to 3 known values: the background temperatures on the east and the west in your southern boundary condition, 250, and Tp is still involved. So you can cancel each equation by the next one, so that you can get the linear set of equations to be solved. So for example, if you divide the first one by 4 and add it to the second one, so it seems that in the second one I will be left up with 3.75 Tp, and Ts is nothing to happen, while you will take quarter of 90, which is 22.5, plus the T2.5. So this is what's exactly stated. Now to solve, you have to continue going to the third equation, divide this equation by 3.75 and add it to the third one, so that you will deal with Ts, and its value is 89. Now when you substitute in the preceding equation, you will find that Tp can be obtained to be 45. So it's a nice gradual change in the temperature from 250 to 89 near the southern boundary, and then in the middle of the domain you have 40. Then the last of the domain you will get Tn about 34. So that's the gradual change, that's the numerical interest that we find, that we can communicate from boundaries, from known values, to extract intermediate values between the boundaries. That's the case. So the boundaries affect the domain. So wherever you are allocated, you will be influenced in the correct sequence. Now, if we deal with the second question to save computer time, as we stated, you have a symmetrical solution around the line AA as shown. So don't let TNE different from TN. They should be the same because you are approaching nothing to give and nothing to lose for the heat when you approach the line AA. And exactly should equal TE. So now when you focus on the temperature just on the left of this line, you will consider that all points just on the left of this line are equal to the corresponding neighbors for these points. So you prepare yourself. Once you approach the line of symmetry, you decelerate your effect, calm down, and do not let something to be exchanged as heat when you come to your stop, because you will start your image from the same point of symmetry, so that to have identical temperatures, you should stop for one time, just to make one temperature as a stop, to decelerate the heat, to let the heat transfer rate equal 0, because if it doesn't equal 0, there is no steady state to be reached at this line of symmetry. And once you let these temperatures equal, so that you will substitute in the equation, just instead of putting 30, just put Tn to get a value that make both of them equal by the equality given. And in the second equation you put instead of TE, you put TP exactly, so that the solution will get TP that makes its value identical at the line of symmetry, and of course identical on the other side of the mirror. So that your only way to make the symmetry is to let the intermediate point between the symmetrical points of the mirror, to let that intermediate point the same, so that you approach gently and you come out from symmetry with the same temperature. And again for the third equation. So when you solve, you will say to the computer, just do not repeat this statement, just say that Ti and n minus 1 will equal Ti and n, so that the subscripts indicate the location in the matrix. So this is the change in the boundary condition that you have to tell the computer about. So in consequence, you will get your profiles in a gentle way, so that your pattern will be tangent to the horizontal lines, so that you have the zero gradient of change along the horizontal directions, because that's the way of making the symmetrical solution, that there is nothing to accumulate on the intermediate positions of these lines. So that this is the way that we did the two ending points, and in consequence the third one became equal. So if there is a flow upward velocity, we may set the neighboring coefficient to be 1 as they are, while we will strengthen the coefficient of the southern boundary. Let us put it to be greater than them. Let's put them put it equal to. If the upward velocity is doubled, you can continue increasing this magnitude of AS to be 4. But I want you to think in detail that if we go into depth, and we know for equal delta X and delta Y and constant thermal conductivity, if we have an upward velocity V, let's look at the original governing equation. We have the temperatures multiplied by the conductivity K. So TW is multiplied by K, TE is multiplied by K, TS is multiplied by K, plus the additional contribution of the convection, which is the mass flux, the term that carries the thermal energy. So it's rho VCP. Tn is multiplied by K, and we know that Tp should be multiplied by 4K and the additional term rho VCP to satisfy the realistic temperatures. So if we divide by K, we will find that TW, its coefficient now is 1, TE, its coefficient now is 1, and TS, its coefficient increases relatively to 1 plus rho VCP over K, and Tn, its coefficient is 1. So for water, if you substitute with thermal conductivity K of 0.6 watt per meter Kelvin, Cp 4180, and the density with 1000, and if the velocity is 0.1 meter per second, you will find that the coefficients of AW, AE, and AN remain as 1, while AS surprisingly goes to 6-digit number, because when we substitute with that heavy water whose density is great, whose thermal capacity is great, we will find that convection is really very strong. It's stronger as we expected. So convection effect is dominant even at small velocities. This is why in our engineering we love convection. We love the currents and the fan to produce air motion, the pump to produce the circulation of the fluid. So you know that in our engineering we have flow going everywhere, so that convection is. Question number 2, there is something very nice and different. We have a flat plate absorber collector, so it's subjected from the upper side with heat flux. So we know that the design of the heat transfer tubes requires the knowledge of the temperature distribution across the plate. So we need to solve this domain knowing the temperatures from beneath. We know that this flat plate is surrounded by air, so that the 30 degrees should surround all sides except the upper surface, because this one is intercepted by the sun rays. Show how we treat the boundary condition if a steady state conduction takes place for such period of time. So in this example, we will see how to deal with the heat flux given. We don't know the temperature of the upper surface. We just know the heat flux coming at these points. If we want to handle this properly, so consider the fluid conduit to have square cross section, so we can deal gently with two-dimensional solution by having the water coming on a flat wall, a square channel, and that the liquid is stationary. We can have such situation where the pump is not running, so that liquid is not moving, and we don't have conduction, we don't have convection. So the water heat capacity can be considered to be huge enough to keep constant water temperature of 30 degrees. So this will be a reservoir of heat. So this will keep the lower temperature to be 30, the lower surface temperature, while the absorber plate rapidly reaches a quasi-steady state temperature, as we mentioned that these boundary temperatures will remain relatively fixed within time. So if you want to deal starting from the north, so the north boundary condition is given as a heat flux, and you will be subjected to the method of writing what's happening for the group of points just below the northern boundary. So we return which says that I know that the collection of Q1, Q2, Q3 and Q4 positively contribute to 0. So the summation of the input heat fluxes are 0, and TW minus TP times K plus TE minus TP times K and TS minus TP times K. And now just add the condition that you know the flux from N to P, you know the flux from the northern boundary. So don't write it in terms of temperature gradient, but just leave it the way it is, because when you consider the solar heat flux as a gain, so you will say that, okay, I know that the thermal conductivity of the steel is 50, and if I know the heat flux of the sun, it's 900, so leave it the way it is. Now you are dealing with a numerical solution just directly without any problem. Another nice question is that we have a free jet region. We have a coolant of water or liquid pushing against a metallic surface so that the jet expands freely in an ambient fluid region before it touches and come into immediate deceleration and stagnant conditions in the stagnant region shown, so that it will continue sliding all over the rest of the metallic surface to get away from the central region. So in this contact we will feel that the water will cool the hot surface of the metal, and it will continue in direct contact. So within the stagnation region we have no fluid motion because we come to stop, and this will bring pure conduction features. And we know the boundary of the jet, that its temperature is known, it's coming from its source, and the surface temperature may be fixed if it's large enough, so that we again we come to a domain whose boundaries are defined. So a cubic steel block at 350 degrees Celsius is quenched by the downward impingement of cool water at 30 degrees. Stagnant conditions are established at a central region of 1.5 centimeter radius, and the thermal boundary layer thickness is 0.7 centimeter. This is the thickness within which the temperature significantly varies from the cool water temperature to the hot surface temperature, so that this is the thickness of the activation region. This is the width of my domain, and I know the radius of my domain region. As the steel block has a huge thickness, its surface temperature slowly changes relative to the water temperature, and this allows me to deal with the quasi-steady state condition. So analyze the heat fluxes across the faces of a discrete. Consider that the metallic surface temperature remains at 350 across the whole surface. And to do that, you will find that in reality you can check what's going to take place as a temporal variation in the temperature distribution. So I am given some instance of time whose temperature distribution is plotted, while I need to know which instant comes before the other. So let's start dealing with this nice interaction. So the central region, I know its radius, its thermal boundary layer thickness, and we have a cylindrical domain shown with R and H. Now what takes place is that the heat flux is exchanged across a circumferential area which varies from a place to place, so that your elements, which starts from 0 radius into larger and larger thickness, this radius will vary and your elemental areas will vary. So that's the only thing in this to consider, so that if you rewrite the equation of conduction so that the K is multiplied by the area and the temperature difference, so that from the left, from TW to TP, you have the inner area, A inner, and from TP to TE you have the outer area, A out, and beneath, from the south, you have TS minus TP multiplied by A lower, and of course A upper is exchanging the heat between TP. So with the trigonometry, we will analyze this small elemental area whose center is occupied by TP. So this is like a rectangle stretched in a curved path. So if you have d theta as the elemental angle variation, so you will have the arc length r1 d theta. So from the western side, so from when you look at TP from the side of TW, you will find that the area for the exchange of heat is the area inner, which is the arc whose length is r1 d theta, and you multiply by h to make this curved area as h times r1 d theta. And the area out, when you look from the larger radius and the curved path between TP and TE, you will find that the area out is going to be h times r2 d theta. While if you look downward or upward, so that you are the heat is crossing that nearly rectangular area, we can see that its length is a curved path whose length is r average d theta. So that's the average arc length passing through the middle of the rectangle, and you have, of course, your width is dr. So it is again area upper, so it's equal r average d theta times dr. So all what you have to do is that you discretize your domain. You will divide by the number of points so that you have your d theta is equal to 2 pi r average. So this is the radius. This is the radius r average, and around a circle whose perimeter is 2 pi r average. So now you divide by the number of points, you get d theta, which split the circle into the number of pieces you want. In other words, you can see that you have 12 circumferential elements whose d theta equal 2 pi over 12, so that you will have 0.52 as d theta. Now, for the liquid in the stagnation zone, the boundary of the south has a fixed temperature of 350. On the northern face, water temperature is 30. We know that the surface temperature is kept at 350. We know that water is coming from its source at 30. While we can say that the exit faces of the water are given at the boundary temperature, or you know that this region of interest start with the background temperature, so that you will leave the background temperature to prevail at the exit sites of that central region. So you will say that this is my domain of interest. I enter with 30. I come downward and I have the metallic surface beneath me at 350, and I know that water starts with a domain in contact whose temperature was at the beginning was 30 everywhere, so that you can update your values at the eastern and western boundaries whenever you want. But you can start with the values in the memory, like to be 30, to watch what will happen for the water when it comes into contact with the hotter surface. So again, whenever we we don't know a boundary temperature, we can rely on the background temperature until this is updated by realistic calculation, so that 30 is the boundary temperature on the eastern and western side. So when water comes into contact with the central region, we know that water immediately touches the central region, so we should expect that always the stagnation region should be cooler than any other region within the solid, because the solid is hot, and the first point to come into contact with water is the central point, is the point of impact. So this point will be subjected to the strongest convection effect, especially when water changes its direction, so that it significantly impinges on the surface and changes severely its direction by 90 degrees, so that there is a severe strain on the fluid when it changes its direction. And of course my cooling capacity is stronger whenever I hit the surface face to face, so that I have the strongest capacity of water cooling. And also because water touches the solid, okay, it becomes warmer, so that at different regions, when water comes into contact with the solid, when it slides, when it continues sliding on the surface and gets into larger and larger radii, water will become warmer, so that it will leave the other regions of the surface at higher temperatures, so that always the central points that will be immediately cooled by water will be at lower temperatures, while any other region will be at higher temperature, because they are away from the strongest convection effect, and because they are in contact with warmer water, not with the original water at the first point. So as water issues from the central region, it becomes warmer as it removes some heat from the metal. It follows that there remains less cooling effect for the outer regions, which thus remain at higher temperatures. However, after some time, we know that water will get the chance to cool all the remaining parts of the solid, so that there is no chance for such discrepancy in temperatures to remain for a longer time, but this discrepancy in temperature will disappear by time, and because the surface temperature will be cooled by water everywhere, so that it will weaken the effect of the warmness within the surface temperature. So such drop in temperature takes place while temperature discrepancy across the solid starts to disappear. Therefore, the time sequence is as follows. The first moment, t equal t1, we have the point of impact immediately cooled to 250, while the farthest point from the point of impact at which water hasn't reached yet this region, because I am in the first beginning moment, so that water hasn't got the chance to slide all over the solid, so that the farthest points are still at 350. Even in the latter moment at t equal t2, you will find that the point in immediate contact, the point of impingement, comes down further to 120, a stronger replacement and stronger cooling by a new mass of water, while still the farthest point still at 350. In the third moment, you will find that now water reached all regions, so that the farthest point dropped to 100, and of course because the points of impact are the most lucky to get cooling, so that they dropped further to 20. So the farthest point dropped to 100, while the nearest point to the impact dropped to 20. So this is the realistic distribution of of the temperature in the spatial domain and in the temporal domain. Now the last question is a different situation of cooling a steel block. I just immersed the block in a huge bath of water, cool water. So now the cooling is coming from below. In the previous example, the cooling comes from the top. Now the cooling starts from below. So such steel block is entirely heated to 700 degrees Celsius, after which it is suddenly immersed into a cooling water bath at 15 degrees Celsius. So such discrepancy in temperature will start to activate some rearrangement of temperatures, so that the hotter region will be restricted to the upper side, because cooling is huge from beneath, so that the lowest temperature will prevail and will push by conduction. Actually, they will decelerate the hotter molecules coming from the above, so that their temperature will drop, so that I will see that the temperature distribution will be like a propagation front of heat, and it is strengthened at the middle while it is weakened at the edges, because the middle is accumulating some sort of potential. However, we will find in two pictures that the cooling is invading from below, is coming strongly to sweep out the domain with lower temperature. It tries to rearrange the temperatures, to redistribute, to make more homogeneous, to make thermal equilibrium. And the more time you give, the more equilibrium you reach. So that I'm asking you which of these instants correspond to to be closer to the steady state solution. So I have two transient solutions, and I'm asking you which one is closer to represent the steady state solution for the quenching of this steel block in the water bath. So of course I see that the one which has the restriction of the higher temperatures is the one that shows longer time of action. That's the closer to the steady state solution, because the disturbance of having the water quenched has propagated by a larger distance, has so much effect, has longer time to act, so that this means that I waited longer time to reach the steady state. So the contour of the low temperature of the 231 has disappeared further inside the block. So this is because the disturbance is coming from the south across a domain whose initial temperature was 700, so that the redistribution takes longer time to restrict these higher temperatures near the upper bound.